Welcome to the chapter on control systems. Control systems are essential in mechanical engineering for regulating the behavior of dynamic systems. In this chapter, we will discuss feedback control, PID controllers, and system stability. These concepts are fundamental for designing and analyzing control systems in mechanical engineering. Feedback control is a process in which a system uses its output to influence its input to achieve desired performance. This is done by comparing the output to a reference value and making adjustments based on the difference, known as the error. An open-loop system does not use feedback to adjust its input. It operates based on predefined instructions. For example, a washing machine that runs for a set time, regardless of the cleanliness of the clothes. In contrast, a closed-loop system uses feedback to adjust its input. It continuously monitors the output and makes necessary adjustments to minimize the error. For example, a thermostat that adjusts the heating based on the room temperature. Consider a room heating system where the desired temperature is set to 22 degrees Celsius. The actual room temperature is measured and compared to the set point. If the actual temperature is lower than 22 degrees Celsius, the heater is turned on. If it is higher, the heater is turned off. This process continues to maintain the desired temperature. A PID controller is a widely used feedback control mechanism in control systems. PID stands for proportional integral derivative, which are the three terms used to calculate the control input. In proportional control, the output is directly proportional to the current error. The proportional gain, represented by Kp, controls how strongly the system responds to this error. The formula is P of t equals Kp times the error, E of t. The integral term deals with the accumulation of past errors. It integrates the error over time to remove any steady-state error. The integral gain, represented by Ki, adjusts the response based on the sum of these past errors. The formula is I of t equals Ki times the integral of the error from 0 to t. The derivative term predicts future error by looking at how quickly the error is changing. It provides a control action proportional to this rate of change. The derivative gain, represented by Kd, controls the response based on how fast the error is changing. The formula is d of t equals Kd times the rate of change of the error with respect to time. The overall control input, represented as u of t, is the sum of the proportional, integral, and derivative terms. The formula is u of t equals Kp times the error plus Ki times the integral of the error from 0 to t, plus Kd times the rate of change of the error with respect to time. Consider a cruise control system in a car. The desired speed is set to 60 miles per hour. The actual speed is continuously measured and compared to the set point. The PID controller adjusts the throttle to minimize the difference between the actual speed and the desired speed. System stability is a critical aspect of control systems. A stable system will return to its equilibrium state after a disturbance, while an unstable system will diverge from its equilibrium state. There are different criteria for stability. BIBO stability, or bounded input, bounded output stability, means that every bounded input results in a bounded output. Lyapunov stability means that small perturbations in the initial conditions result in small deviations in the system's response. Stability can be analyzed using various methods. The root locus method is a graphical method for examining how the roots of a system change with variation in a particular parameter. The Bode plot is a frequency response plot that shows the gain and phase of a system as a function of frequency. The Nyquist plot represents the frequency response of a system and helps in determining the stability using the Nyquist criterion. Consider a pendulum. When the pendulum is at its lowest point, hanging straight down, it is in a stable equilibrium. If it is slightly disturbed, it will oscillate around the equilibrium point and eventually return to it. However, if the pendulum is balanced at its highest point, inverted, it is in an unstable equilibrium. Any small disturbance will cause it to fall away from this point. Understanding feedback control, PID controllers, and system stability is crucial for designing and analyzing control systems in mechanical engineering. These concepts help ensure that systems behave predictably and maintain desired performance despite external disturbances.